And then third, is very important, is we want to make sure we validate against our requirements early in the process. Okay? So this is a wish list. This is what we would like to do. We don't always do that in our traditional design flow, but theoretically, in model-based design, this is what we do. So what does that mean in model-based design? In the design phase, right, model-based design, as I said before, is about using a model to represent a system. And this model has components. It has a lot of components. And those components can link to your paper-based requirements. So if your company mandates that you write system-level requirements, you can link each of these blocks to those lines of requirements, line to line. Because you're using the same model to elaborate in detail, and because these models are executable, you can run fast simulations, and you can iterate several iterations and design all of your design space. Okay? And by executable, what I mean is you can simulate this model. You could look at the results. So it's not just a pretty picture. You can actually simulate it. Now, many of you are looking at this and say, oh, that sounds very abstract. I don't really know what you mean. So let's take a look at an example, right? This is an actual example of one of our customers building a model in the design phase. This is a wind farm. Okay, this is a simulation of a wind farm. And actually, our consultants created this model for our customer. It's got 40 wind turbines. And in the design phase, the system engineers would come and create this model. They would lay out the blocks, define the interfaces, link these blocks up to the requirements, and simulate the model. When it comes time to design, the algorithm engineers, the mechanical engineers, the electrical engineers then go into these blocks and really elaborate these models into something more real, more practical, something more useful. Right? And then, again, simulate. And as they're doing this, they're really evaluating their design space. They're really looking at all the different options, looking at all the trade-offs. It's a very, very powerful concept. Now, how did our customer use this model? How did our customers use this model? Our customer was able to leverage the output of this model, this realistic and accurate simulation results, and they used this for very strategic business decisions. They used this model to be able to figure out how to scale their wind farm, how to deploy their wind farm. And they did this all before committing to hardware. They were able to do it all in software. So you can imagine the cost savings there. So that's a little bit about sort of an anonymous example, but let's look at some real examples also, right? An example from Philips. Philips, we all know Philips. It's a Dutch company, Dutch electronics company, right? And here, they were very successful with the design aspect of model-based design. They made one-piece surround sound systems, and one of the engineers is so happy with their solution that they gave us a testimonial. They said to us that Simulink is crucial for the creative aspect of our work. With Simulink, we do not have to worry about the details of implementation while we are exploring design ideas. When we have an idea, we can simply model it in Simulink, simulate it, listen to it in real time. This is very beneficial for us. And this is one of the largest electronics companies in the world. Right? So that was a very nice example. And that was design. What about implementation? What about the implementation phase of model-based design? You're going to see a lot of talk about implementation today. We're going to be talking about a lot of capabilities that we added in this area. But what does it mean in model-based design? Implementation in the traditional sense, implementation in the traditional design flow, what do? We took a paper-based document, we ripped it in different pieces, we handed it off to the DSP engineer, we handed it off to the hardware engineer, and they started writing Verilog, they started writing C, right? And typically, that goes back and forth. There's a lot of issues there. But in model-based design, implementation is about doing all the implementation work up in software, up in the design state here. We do all of our fixed point design, we do all of our target-specific constraints and considerations, all in our model. This model here, we call Simulink, allows us to incorporate all of those capabilities. And when you're ready to implement, we use some technology to allow us to do automatic code generation. So we can automatically generate these implementation codes, which we'll talk a lot about today. Now, many of you probably can imagine the benefits. Reduce time of implementation. If you needed to code your algorithm in C or Verilog, code your system in C or Verilog, it might take weeks, perhaps months. But with automatic code generation, in a matter of seconds or minutes, you can have your code. You can start verifying that code. So, reducing time of implementation. Avoiding manual coding errors. This is key, right? The code that's generated by our code generator generates the same code every day of the week. Tomorrow, if you decide to generate the code, it's the same code. But if you ask me to write a filter or FFT, it's going to be different next week than if I write it today. And it all depends on how much I slept the night before. Right? You guys know that. So that's a great benefit. So really ultimately, what we're talking about is focusing more on innovation. We're really focusing more on the front end of our design here. Innovating. Innovating is the word that we're using a lot today, right? Rather than focusing on the semantics. So that's what implementation is about. I'd like to talk to you, I'd like to focus in on one user story that we have. And we're going to go back to the user story that Todd highlighted, which is Faraday. Faraday, most of you know probably Faraday. It's a Taiwanese company here, right? And they wanted to make flash controller, silicon IP. They used Simulink to create a behavioral level model. They elaborated that model. They automatically generate the code. They generated HDL, Verilog code, and targeted an FPGA for prototyping. And eventually that algorithm made it down to an SoC. That's a very, very powerful workflow. That's model-based design. Now, I'm quite proud of this user story, actually, because it's, as somebody from Taiwan, right, I am proud that a company from Taiwan is leading the way in innovation around the world. And they're really on the cutting edge. Our good friend Ken Chen told us that Simulink is an excellent environment for integrating, simulating, and exploring design architectures. So congratulations, Faraday. Verification. Verification is a key part of model-based design. Verification in the traditional flow, as I described it earlier, verification happened all the way at the end before. Errors were caught very late. But with model-based design, the key is the executable model. The executable model that allows you to simulate that model continuously. Every time you make a mistake, or every time you elaborate and make a design change, you could quickly simulate that model, and and you catch the error right away. So this is the notion of continuous verification. You're always verifying as you're making design changes. The benefits here, of course, is that the errors are caught much earlier and they're fixed as they're being introduced rather than at the very end. And this reduces a lot of unwanted engineering effort at the very end of your design flow. So that's verification. And in a nutshell, that's what model-based design is about. Todd alluded to this earlier about GM. GM, one of the most famous automobile companies around the world, right? They epitomize the usage of model-based design. Let me just kind of go through some of the things that they did. So GM created a model that was millions of blocks large in Simulink. GM used model-based design to do automatic code generation, and they released their software, production software, every 6 weeks. And this model was created by hundreds and hundreds of engineers around the world, 16 different locations. So they were very, very successful with the complete model-based design flow. So the question is, if GM could do it, why not the rest of us? Right? So that was model-based design. That was the flow. I'd like to talk to you a little bit about one of MathWorks' models. Right? MathWorks has a model, we say continuous improvement. We're always looking to improve our products, the workflows, etc. Right? So right now, I'd like to talk to you a little bit about what we've been doing to improve on this workflow, this model-based design workflow in 2011. In the past year, we've introduced capabilities in all phases of model-based design. All right? So in the design phase, that's up here, we've introduced something called system objects in System Toolbox. In the implementation area, we've introduced MATLAB Coder, capabilities for AutoSum, capabilities for FPGA workflow. And in the verification area, we've added capabilities for certifications and polyspace. So at a very high level, these are some of the things that we've added. Now I want to talk briefly about some of these capabilities. We're going to talk a lot more about this, and we're going to see these capabilities in action in the sessions today. All right? But the first capability, very exciting capability called system objects. This is really a new paradigm, programming paradigm at the MathWorks in MATLAB. Okay? It's an object-based approach for dynamic system design in MATLAB. This allows us to more naturally represent dynamic systems in MATLAB. It's an object-oriented approach. Allows you to more naturally represent dynamic systems in MATLAB. It improves your simulation speed and efficiency. And finally, it gives you a path to C code generation from MATLAB. It's fully integrated with this other feature, which I'm going to talk about next. So that was a little preview. That's a little teaser. Now, where do these technologies live? Well, if you're a savvy MATLAB user, many of you are probably very savvy at using MATLAB. You know, when you type the command VER in the MATLAB command prompt, a whole list of products come up, right? You guys know. Yeah, people are shaking their heads. That's good. A whole list of products come up. Well, if you used to have Filter Design Toolbox, and if you used to have Signal Processing Block Set, in the latest releases, you won't see those anymore. We've combined those two products to simplify our productization, and we're calling it DSP Systems Toolbox. Okay, so these two products have been combined, and guess what? Conveniently, we added new capabilities for the DSP Systems Toolbox, such that it includes system objects. So let me make it clear. All of the functionalities that we had before here, they still exist, the function-based capabilities. We repackaged them, and we added new capabilities, something called system objects. All right? Similarly, we've done that to some of our comms products, our video products, and for those of you that are working on radars, working on advanced communications, we've also added a phase array systems toolbox. These are some of the new products in the signal processing and communications area. Next, for the implementation area, we've added a very exciting feature that a lot of our customers are excited about. This feature allows us to generate C code from MATLAB. All right, you can generate C code from MATLAB. Many of you probably have some ideas now what you want to do with that capability, right? So let me tell you the different kinds of C code you can generate from MATLAB. Well, first of all, if you have your own corporate simulator, if you have your own C-based simulation environment, you can integrate the code that comes out of MATLAB Coder. We generate libraries. We generate .lib files. Okay? Compact, reusable libraries. So that's the first use case. Secondly, if you do PC-based prototyping of your algorithm, meaning if you want an executable, you can generate that as well. You can generate a standalone executable from MATLAB Coder. Number 3, if you want to target embedded processors, many of you work on embedded systems. If you want to target embedded processors, you can use MATLAB Coder to generate fixed point embeddable C code, standalone .c files. Lastly, acceleration. This is a very, very big topic for a lot of our customers. With MATLAB Coder, you can generate C, and it'll automatically generate MEX wrapper so that you can bring that compiled code back into MATLAB, you can call it, and speed up your MATLAB simulation. Okay? So these are the 4 different use cases. And finally, another thing in FPGA, or another thing in the implementation area, is the FPGA workflow. The FPGA workflow, there's a new capability called FPGA in the loop. FIL, we call it. Okay? This product, or this capability, is embedded in one of our products called EDA Simulator Link. And effectively, this allows us to run co-simulation with hardware boards, development boards. You can have Simulink driving a hardware board and running co-simulation. So if you ever wanted to do, for example, fast simulation, simulation acceleration, you have a board, you can automatically target it, run your code, and actually communicate through this Ethernet data transfer, all the data live. All right? So at this point, there's one more feature that called parallel computing that I wanted Todd to speak about a little bit. This is his area of expertise. Get it off to you.
So parallel computing, another way to accelerate. It's all about what I said earlier, getting better, faster, cheaper. I want to get better answers, better simulations, so I have to increase my accuracy in my simulations. I have to increase the amount of calculations I have to do. I have to work with more data to get more accurate answers. I want my answer faster. If I'm going to innovate, if I'm going to stay ahead of my competition, I need my answer faster. I can't wait 6 weeks anymore. I need it in a night. And cheaper. Well, parallel computing uses lots more computers, so it's not necessarily cheaper, but computers are cheap. So it's taking advantage of the innovation other people have done for you. For 2 reasons. One, speed, as we're showing here, large computation pools. I want my answer now, not tomorrow. The other reason, large data. Who here has ever gotten that wonderful out-of-memory error in MATLAB? How annoying is it? Parallel computing can allow you to link together the memories of many computers. You can deal with your large data. That out-of-memory error goes away. That's what parallel computing is about. In the MathWorks perspective, you want to use the hardware resources you have available, whether it be your desktop, a GPU, a single processor, a multi-core processor. Kind of actually hard to find a single core, single processor anymore. Even cell phones now are multiple core. Multiple processor, cluster clouds, but we want that to be transparent to you, the user. We want you to focus on your problem. What is the science? What is the thought? Not worrying about the semantics of parallel computing. We want it to be easy for you. That's what we'll be showing today, how easy it can be for you to go from any one of these resources to the other, to get your answer faster, and do what you need to do.
So this is actually it's coming to the end of our talk, and I think Todd, I speak for Todd, but I think both of us have enjoyed talking to you about how MathWorks is helping drive innovation. Now, for the rest of the day, we hope you enjoy your day, but I'd like to just introduce the sessions real quickly here. Maybe Ginny can help me out as well. But basically, there are 3 tracks. There are signal processing and communication tracks in A, embedded control systems design and automation, and energy. Is this track B?
Yes.
This is track B. Data analysis in technical computing and image processing. That's C. So please, talk to us. Enjoy the tracks. Talk to the Terasoft attendees here. And talk to the rest of the attendees here. And thank you.